Right, welcome to lecture number 58. This week 12, lecture number 3. So now we move on to the last topic of this course, which is entanglement in mixed states. And certain backgrounds were required for that, so that's why I waited till the end. So I will introduce this subject using an example. So the example is, supposing I have a 2-qubit system. Okay, 2-qubit spin system. So I have something called the Heisenberg model. Okay, it's a very famous model of 2 spins, and H is J S. So generally it is Ij with nearest neighbor interaction Si dot Sj. But what I am going to do is take just 2 spins. So which is equal to, simply for 2 spins, it is simply J S1 dot S2. Okay, where your S1 is equal to I Sx plus J Sy plus K Sz, sorry, and S2 equal to I, sorry, this is S1x spin 1. I am putting the index on top, and this is I Sx2 plus J Sy2 plus K Sz2. Okay, now interestingly, this is a 2-qubit system. Okay, so Si is simply Si is simply h bar by 2 sigma I, where I equal to x, y, and z, or 1, 2, 3, whatever. 1, 2, 3. The 1, 2, 3 is x, y, and z only. Okay, so this is equation number 1. Okay, and what we have here is very interestingly, we have the Sx. Oops. So Sx is, see, Sx is supposing, say, h bar by 2 sigma x and 0, 1, 1, 0. Sorry. 1, 0, but remember that this is a 2-qubit system, so the dimension of the Hilbert space is basically higher, in the sense that it's 4 by 4. So this is a 2 by 2 matrix. So I have to extend it to 4 by 4, and what I do is very simple, is Sx1 will be written as sigma x tensor identity 2, and Sx2 will be written as identity 2 tensor sigma x, where identity 2 means 2 by 2 matrix. Okay, so which is simply 1, 0, 0, 1. All right, so now let's generate Sx1. Okay, if we want, we can set h bar equal to 1. Okay, so let us set h bar equal to 1, become like particle physicist. So Sx1 is 1 by 2 sigma x tensor identity, and this is 1 by 2 0, 1, 1, 0 tensor 1, 0, 0, 1, and that's basically, in our notation, is 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0. Okay, similarly, your Sx2 is simply half of identity tensor sigma x, and that's half of 1, 0, 0, 1 tensor 0, 1, 1, 0, and this comes out to be half of 0, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, and 0, 1, 1, 0. Okay, right, now I have to evaluate Sx1 dot Sx2 for generating the Heisenberg Hamiltonian, and that is simply 1 by 2, 1 by 4, because half and half, 0 0 0 1 0 0 1 0 0 1 0 0 1 0 0 0. Okay. Similarly, we generate sy1. So similarly, we generate sy1 dot sy2, sz1 dot sz2. Okay, right. So the Hamiltonian is j by 4, and I just add them up. Add up sx1, sx2 plus sy1, sy2 plus of sz1, sz2, and obtain 1 0 0 0 0 minus 1 2 0 0 2 minus 1 0 0 0 0 1. Okay, great. So this is, let's say, equation number 2. Now, in general, in a Heisenberg Hamiltonian, we also have a Zeeman term. Okay, Zeeman term. So the Zeeman term is simply sum over I as Zi. Okay, so basically, for our two spin case, it is simply, or there's a B term. It is simply B of Sz1 plus Sz2, and Sz1 is, as you know, half of sigma Z tensor identity, and that's basically 1 by 2 1 0 0 0 0 1 0 1 0 0 0 0 minus 1 0 0 0 0 minus 1, and your Sz, this is Sz1, and similarly your Sz2 is equal to half of sigma identity tensor sigma Z, and that's half of 1 0 0 0 0 minus 1 0 0 0 1 0 0 and 0 0 minus 1. So Sz1 plus Sz2 is simply 1 0 0 0 0 0 0 0 0 0 0 0 and 0 0 0 minus 1. Okay, let's say this is 3. So if we combine the matrix, I'm going a little fast because these are very trivial things. If we combine the matrix from equation 2 and 3, okay, so the Hamiltonian, which is S1 dot S2 j by j plus B S1Z plus S2Z. So this comes out to be the net Hamiltonian is j by 4 plus B 0 0 0 0 minus j by 4 j by 2 0 0 minus j by 2 minus j by 4 0 and 0 0 0 j by 4 minus B, right? And in absence of magnetic field, okay, this is equation number 4. In the absence of magnetic field, we have, so basically, okay, let's if we just take j by 4 equal to 1, yeah, and b equal to 0. Actually, this is just trying to see what the Hamiltonian can look like. So I just simply, this is a very simplified picture, so I just simply write 1 0 0 0 0 minus 1 2 0 0 2 minus 1 0 and 0 0 0 1. Now notice that this has a, so let's change the color. This has a X type structure, which means the element here, 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 and here, 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 here. Okay, so undo, 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 undo. Now I will draw, oops, I will draw something called a block diagonal form. So this matrix has a block diagonal form. So if you notice here, right? Okay, so this term here and this term here anyway form the diagonal matrix because this is 0 0. So basically, yeah, using the mouse I'll show this is 0 0 0. This is also 0 0 0 0 0 0. So basically what I have is a very nice structure of this X type structure, this block diagonal form. So the eigenvalues, I can straightway read off the eigenvalues. So let me give a slightly different color. So this is in the diagonal form. This is also in the diagonal form. So both are eigenvalues. So I have, say, lambda 1 equal to 1 and lambda 4 equal to also 1. Okay, but I don't write it as lambda 4, I'll write it as lambda 2 only. So lambda 2 is 1. And then I have this block thing. Okay, I have this block diagonal form which I have to undo, which I have to solve. And the block diagonal form is -1 to -1. And this is the block diagonal form, and it's very easy to diagonalize this, and I am not going into that. So I have here some one of the lambda, say 3 equal to 1, and one of the lambda 4 equal to -3. Okay, so there I have a threefold degenerate. So basically, let's go back to it. So we have a threefold degenerate rate lambda equal to 1, and another one lambda 4 equal to -3. Now remember that we had put j by 4 equal to 1, right? So here is j by 4 equal to 1. We had put that. So if I substitute that back, so then I have the threefold generate state as so this would be minus of 3j by 4, and this would be j by 4. Okay, so threefold regenerate j by 4 and -3j by 4. Now just by looking at the uh, matrix, I have that if it is this, then the eigenvalue is simply up. Okay, and if it is this, then the eigenvalue is simply eigenvector is simply, so this is simply down. Now you know the up is simply, if you have a column matrix 1 0 0 0 0, and down is ulta. So basically 0 0. Okay, so all right, it is not coming here. So this is equal to 0 0 0 1. Okay, so right, so these are the two eigen vectors that we can identify. And for lambda 3 equal to 1, so basically your E3 equal to, okay, let's call this as E1 and this as E4. And once we diagonalize this, your E3 and E4 are not that simple. So your E3 is now a column vector ones. So basically 0 1 1 0, and I have a normalization 1 by root 2, and this is nothing but 1 by root 2. So this is nothing but 1 by root 2 up down. one of the bell states plus down up. All right, and lambda 4, sorry, lambda, this is lambda 3. Okay, let's call this as lambda 4 only. Yeah, this is lambda 4, which is minus 4. So basically for lambda 4 equal to minus 3, and your E3, sorry, E4 equal to 1 by root 2, 0, 1, minus 1, 0. And this occurs naturally, even though I don't have to put it in. So right now, so this occurs naturally, and this is an entangled state. This state is simply 1 by root 2, up, down, minus, down, up, which is basically 1 by root 2, 0, 1, minus 1, 0. This is the singlet state. Okay, so this is called the singlet state. So these are entangled state. Okay, very good. So if I were to put in back j by 4, then I have this, like, let's say energy of 1, eigenvalue of 1 is j by 4 plus b, and j by 4 plus b. So this corresponds to down, 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 which is basically 0, 0. It's a separable state, and E2 is equal to j by 4 minus b, and this is simply up, up. Okay, and right, or this is, I am really sorry, I think I made a mistake here. Yeah, this is up, up, this is down, down. Okay, and this is 1, 1, let's say, and then I have E3 equal to also j by 4, and the wave function is psi plus. Okay, the original bell state, and E4 minus 3j by 4, and here this is psi minus. Okay, very good. Now let us construct something which is called the thermal density matrix. So let us construct the thermal density matrix, and that is given as rho equal to 1 by z. Z is the partition function, which is trace of rho. This is simply trace of rho, as rho has to be 1, and I have sum over I e to the power minus of beta ei, and ket bra of ei. Okay, so let's say this is equation 5. So what's so good about it? This is the definition, and your z is simply trace of rho. Okay, this is just a normalization. So I do get rho. Okay, back to red. I do get rho equal to, so 1 by z. So if I expand that sum over e to the power I, beta I, and ei, I have e to the power plus 3j by 4 times beta, and I have beta, and I have psi minus, which we know is a maximally entangled state, plus e to the power minus of beta j by 4 minus b with magnetic field non-zero, and I have up, 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 plus e to the power minus of j beta by 4, and sorry, this is 3j by b, beta, this is beta, and this is minus of j beta by 4, but here you also have the field term because in the fourth one, and this is right. Okay, this is sorry, the beta is here also. Beta b is equal to j by 4 beta is common, minus j by 4 plus beta. Okay, plus b beta. Now so this fellow will correspond to the okay, sorry, okay, let me just erase this. There's a lot of cumbersome it's happening, so let me write it down. So this is done, 3j by 4, then j by 4 is done, then another e to the power minus of e to the power minus of beta j by 4, and that's psi plus plus e to the power minus of beta j by 4 plus b, and that has psi minus, I'm sorry, that has yeah, that has down. Okay, so now we know that psi, let's say I have psi minus the singlet. Now we have a state where j, okay, so if we have antiferromagnetic correlation, so then j is greater than 0. Okay, and then therefore minus, so the ground state is minus of 3j by 4, okay, which corresponds to psi minus. Okay, and therefore if we construct the density matrix using psi minus, this is simply was when we calculated one Neumann entropy, etc., and this is what we do, and this comes out to be 1 by 2 0 0 0 0 0 1 1 0 0 1 1 0 0 0 0 0. Okay, so right, I think I have made a mistake here. 1 second. Yeah, it is -1 here. It is -1 and it is -1. Okay. Now this is a pure state, so it is idempotent. So the there is only one wavelength lambda 1 equal to 1, and all other lambda 2 equal to lambda 3 equal to lambda 4 equal to 0 for this particular case, right? So now we know that this is a maximally entangled state. So at t equal to 0, so basically when beta goes to infinity, t equal to 0, beta goes to infinity, this reduces to the ground state. Okay, just the ground state, because if you take beta j by 4 outside, and then you expand the other one, so then you put beta goes to 0 inside, so I have only psi minus left, so it's a pure state basically at 0 temperature. Okay, right. So at t goes to 0, beta goes to infinity, so the e to the power minus infinity vanishes. So basically, and in such circumstances, what we have is effectively, okay, the only psi minus, so it's a pure state, so it's a maximum. So at t equal to 0, system is maximally entangled. Now if I take the full row, it can be written as 1 by z, where I'll tell you what is 1 by z, to the power minus of j by 4 minus of b times beta, and somewhere here, yeah, somewhere here you have e to the power minus of j by 4 plus b times beta. Okay, so these two are gone. Okay, this is 0x type, right? 0 0 0 0. Okay, and this is also 0, and this is also 0, this is also 0, this is 0 0. So what we have is again that block diagonal form, and this time I'll write this with blue. It's a little tricky. So you have 1 by 2 e to the power 3j beta by 4 plus of e to the power minus of j beta by 4. Okay, so this is 1 by 2 e to the power j beta by 4 minus of e to the power 3j beta by 4. Okay, close. Again, so this is a Hermitian operator, so it's just there will be something right, and the z, which is trace of row, which is this, the partition function is given as e to the power minus of j by 4 minus b beta plus e to the power j beta 3j beta by 4 plus of e to the power minus of j beta by 4 plus e to the power minus of j by 4 plus b times beta. All right. So then, so the next thing is what we do is what we put this to be 0. Okay. So now what happens? What happens at t goes to infinity? So then beta goes to 0. Okay. So once beta goes to 0, then my matrix reduces to, so basically the matrix reduces to a diagonal matrix. This is 1 by 4, and I have 1 1 1 1, and all other terms are 0. Okay. So now what is the entanglement in the system for such a case? So such a matrix can be written as, so I have this 1 by 4, I can write down 1 0 0 0, all other terms 0, plus 0 1 0 0, all other terms 0, plus 0 0 1 0, all other terms 0. So 4 diagonal matrix plus of 0 0 0 1. Okay, and all other terms 0. Okay, so this can be further broken. This can be further broken into 1 by 4. Okay, and this is simply 1 0 0 0 tensor 1 0 0 0 plus. So this is system 1, this is system 2, 1 0 0 0, system 1 tensor 0 0 0 1. Okay, and there are two more terms, plus of 0 0 0 1 tensor 1 0 0 0 plus 0 0 0 1 and tensor 0 0 0 1. Okay, I close the bracket. So these are all Hilbert space 1, Hilbert space 2, Hilbert space. So this is the sum. Now notice that this sum is actually interesting, because what I have is a product of two density matrices, in the sense like 2 by 2 density matrix. They're all density matrices because they're diagonal. A, B, they have only one eigenvalue, and that's 1. Okay, so so all these, so this thing is a sum, a product of density matrices, product of what type of density matrices? 2 by 2 density matrices which belong to Hilbert space 1 and Hilbert space 2. Okay, now this is the interesting thing. So this is written as something called convex sum. So let me tell you, this is a separable state. Whereas at t equal to 0 it was an entangled state, t goes to infinity is a separable state. Why? So how can you examine this and say this is a separable state? So because I have this row 1, 2, okay, so this row is actually row 1, 2. Row 1, 2, which if it can be written as sum over I, pi, row A, okay, yeah, so okay, row 1 I, tensor row B I, okay, sorry, row 2I. Let me change a little bit of notation. So let this be let the two Hilbert spaces be called AB. It's easier to represent. So IA and IB. Okay. So if this holds such that for all pi greater than or equal to 0 and sum over I pi equal to 1, then this will hold. So now if you see, so pi, so in this particular case I have 4 pi's, and what are the pi's? So basically I have all of them is equal. P1 equal to, P2 equal to, P3 equal to, P4 equal to 1 by 4, and P1 plus P2, P1 plus P2 plus P3 plus P4 is equal to 1. So this is called convex sum. Convex sum. In the next class we'll take it up further. So what is convex sum? So let me just end here by saying that convexity is if we have a matrix like this which has a sum over I pi row I A tensor row I B such that all pi's are positive and sum over I pi equal to 1, then this is called a convex set. Okay, convex set. Okay, and if the density matrices are of the type which belongs to a convex set, then if we can write it this way, then this type of density matrices are called separable density matrices or separable states, simply separable states. Okay, so we end here.